everybody. Welcome to our first town seminar of the fall semester. Noel Gutierrez-Brizuela. Noel did his undergraduate in physics from the University of Guadalajara in Mexico. And then after that, did both his master's and his PhD in oceanography at UCSD at Scripps Institute of Oceanography. And so he's just continually moving northward, it seems. And so he's now currently at Lamont Doherty Earth Observatory as part of Columbia University, where he's been for just about a year or entering a year. Where actually that's how I've learned to meet Noel. Is actually he's a postdoc on one of the projects that I have with some Columbia colleagues. So at Columbia, he mostly works with Chai-Yang Yi, Susana Camargo, and Adam Sobel, as well as Richard Seeger, kind of working on project that's focused on the role that ENSO plays in future projections of tropical cyclone risk, but also thinking about biases and issues with ENSO variability and how it manifests in climate models as well. And I think maybe we'll hear a little bit about that. I just one additional thing I noticed when looking over Noel's background is he's quite interdisciplinary for somebody so at this point in his career. And you can even tell by both his PhD work, but also now the group that he works with at Columbia, he's always kind of straddling, I would say, the kind of atmosphere ocean side of things. But I think you'll find from his talk today that he's really, he is an oceanographer, but he's focused on those things that are coupled. And I was joking with him before that one of the things we'll have to talk to him about at lunch, because we won't hear about it in a seminar, is that I noticed by looking at his Google Scholar that he's written a couple papers around the COVID-19 pandemic and the spread and prediction and movement of COVID and other things, which we can ask. He said there's a good story, so that's even more bait for you to make sure you come to lunch after the seminar. But with that, I'll turn it over to you, Noel.
Wonderful. Thank you so much. Thank you all for coming here. And as Kevin said, I won't talk about health. I will talk about the ocean and the thermocline. Now, most of us, when we learn about the ocean, we learn about this version of the ocean here, in which the ocean is composed of layers, and each layer has a different temperature. As you go deeper, the layers get colder and colder. And the way most people look at the ocean is like each one of these layers is sort of independent, and the only way you can change any given layer is by changing the air surface fluxes of momentum or heat in the area where that given layer meets the atmosphere, right? So under this view, a layer like this one that I'm pointing at, if it's not directly reaching the surface, then it's isolated and it's doing its own thing. So that's how most people learn about the ocean. But then, if you go and talk to a small-scale oceanographer, they will have in their head a very different vision of the ocean. And in this vision, the layers of the ocean are not very easily defined, right? There's not a concrete separation between water that's 25 degrees and water that's 24 degrees. And also they're always exchanging information, fluid, momentum. And so here what you're looking at is this is acoustic backscatter data from the Jim Moon, and essentially you have this soliton propagating onto a shore, and along the interfaces between layers of different temperature, there's active turbulence and overturning that is allowing the different layers of different density to talk to each other. The issue, so now we have these two views of the ocean, and that generally is okay. But the issue that I have with this distinction is that when you look at theories of climate variability, they're all constructed on this view of the ocean as separated layers that don't interact with each other. Perhaps with the exception of some work in the Atlantic, but when we look at the Pacific, people mostly think about these layers as separated. And I think that the best example of it is El Nino. So El Nino in this, the classic zodiac cane model that was the first one to predict El Nino activity, we have a layer of warm water that meets the surface and that is mostly, sort of tilted upon the Western Pacific. And then below that, we have a thermocline that separates it from the cold water. And El Nino is the sloshing of back and forth of the boundary between those warm and cold layers, right? So that people think about El Nino in this way that separates the two layers. But in reality, we know that the turbulent mixing between the layers, right, creates this diffuse leaky boundary between the two layers. Are always exchanging information, and as you bring the cold water closer to the surface, even though the cold water is not, or layers that are not directly seeing the atmosphere, they can indirectly be affected by the turbulence that takes energy from the ocean surface down into, say, 100 meters depth via turbulence. And that's what we're seeing here in this data set where Jim Moon put turbulence sensors in the equatorial Pacific for several years. And where you see these colors, that is a measurement of the downward turbulent heat flux that is presented here as a logarithm 10. So you'll see many long periods where there's green or where there is red. Wherever there's green, there's about 100 watts per meter squared of heat going across that level. So if we look at this particular one between 2008 and 2009 at 7 meters depth, you'll see for months you have 100 watts per meter squared going down across that level. That is almost equivalent to exposing the water at 70 meters depth directly to the atmosphere for months at a time. Even though we would usually think of this water as separate from the water that is meeting the ocean. So what I'm really trying to show you here is this view of the ocean as separated layers is it doesn't really hold up to the way we know now with high precision instruments that the ocean works. And in particular, what I'm going to talk about today is I'm going to talk about the mechanisms that allow the atmospheric forcing to impact subsurface ocean properties. And so I'm going to talk about the processes that control that sort of leakage that we see through the thermocline. I'm going to tell you about how that leaking impacts background climate. And there's also some inspiration on needing to nail down these two first questions before we can start and try to understand ocean change with global warming. As we're essentially global warming, we're imposing radiative warming in the atmosphere, and then that warming is going to have to diffuse some way its way down into the ocean. And the two mechanisms that I will focus on today to induce this energy transfer across the thermocline are near inertial waves and upwelling, which are kind of analogous in a way. So in order to have communication between layers of the thermocline, you need to use energy, kinetic energy that is spent in turbulence. So you have energy, and then you have turbulence. That kinetic energy is turned into internal energy and potential energy. And so these two mechanisms are analogous in the sense that near inertial waves are a mechanism for atmospheric wind-driven currents to make their way into the deep ocean. So you have a storm, shakes up the mixed layer, that momentum slowly propagates into the deep ocean. So you're bringing the energy from the atmosphere down towards great depths. And in turn, with upwelling, you are bringing the thermocline up towards the surface where there's more kinetic energy to drive turbulence. So we'll see those two analogous scenarios. Now this project it was part of my PhD at Scripps, and I did it in collaboration with folks at Scripps and also Oregon State. And the whole this whole project really is counterintuitive, or you gotta set it up, because usually when we think about tropical cyclones, we think about their destructive effects, right? They become a poster child of climate change. They're featured on Al Gore's documentary. And tropical cyclone immediately brings, destructive effects, flooding, et cetera, et cetera. And we rarely stop and think that maybe tropical cyclones are a crucial force in shaping the global climate system. That their effects last longer and expand wider than a few days in places that flood. Now in this, there's a bit of an anecdote, but actually the Mayans, they put together in the 1500s, the Mayans see that some crazy monk is trying to burn all their books, right? So they get together this council of smart people to write a book that summarizes the most important knowledge that the Mayas hold in these textbooks that are being burned. And in page 1 of that textbook, called the Popol Vuh, the People's Voice, in page 1 it says, hurricanes are the heart of the atmosphere and they bring life onto the land. Page 1, they see already hurricanes as a crucial force in shaping the climate system. And that was the wrong button.
You got it.
Oh, there we go. So that's the Mayans, and then 500 years later comes Kerry Emanuel and gives us a more precise theory of exactly how tropical cyclones shape the climate system. So usually, pretty much always when a tropical cyclone goes over the warm tropical oceans, it leaves behind a wake of cold water. The way this works is initially you have, so these are temperature profiles in a cartoon that Kerry wrote. So you have a shallow, very warm mixed layer that has a temperature gradient below it. Then you have tempestuous winds for several hours, and much of the energy that the wind puts into the ocean is used to drive turbulence that mixes the warm water at the top with the colder thermocline. So by the time the storm is gone, you have a deeper mixed layer that has a cold anomaly at the surface and a warm anomaly below that. So this is sea surface temperature data after Hurricane Irma. And so this, again, it's a cold anomaly. But if you look at this cartoon and realize that much of that cooling, really most of that cooling happens via turbulence, then you'll realize that below this cold wake, there is a subsurface warm wake. Now, what Kerry Emanuel said is, you have this warm wake. In the weeks after the storm, you'll have the sun that comes and shines again. That'll re-stratify the upper ocean. And by the end, you will have this warm anomaly that is locked into the upper thermocline, and that excess heat is going to be available to be transported onto the exotropics. So this way, Kerry Emanuel argues that tropical cyclones enhance the ocean's ability to absorb heat by putting heat from the mixed layer into the thermocline. And then once that heat's in the thermocline, it's locked in for a long time and it gets advected to the exotropics. And via this mechanism, he says tropical cyclones are shaping that climate. That's a very exciting idea. People go and find ways to test it and quantify what that heat contribution might be. Generally, estimates range between these two numbers, 0.15 and 0.6 petawatts, which is between 10 and 40% of heat transport out of the tropical Pacific. So if this is in fact happening, and the tropical cyclones are in fact enhancing the ocean's ability to absorb heat, then we better know how that actually works, right? And what the potential consequences are. Now, one of the most exciting potential consequences in the literature is here in this paper by Alexei Fedorov. He says, okay, imagine that you have a climate state in which there are 5 times more tropical cyclones than we have currently. So the areas with a lot of cyclone activity, their thermocline will be more leaky, and there will be more heat making its way down from the surface into the deep ocean. what would happen if that was the case. So here in this upper plot, we see the historical cyclone tracks. And you'll see that the Western Pacific has the greatest density of cyclones and also the highest intensity cyclones. When you increase the turbulence, the ocean turbulence that is caused by those cyclones in that area, what Alexei finds is that you have a bunch of excess heat that enters the deep Western Pacific, then gets transported to the eastern equatorial region, and that induces temperature anomalies that are similar to those caused by El Nino. Then he runs the opposite scenario in which he thinks about an ocean that is permanent, that permanently looks like El Nino, and then he finds that in that ocean you would have 5 or so times more hurricanes that we see in current climate. So they proposed this interaction in which you increase cyclone tracks, that changes the distribution of heat in the ocean. That distribution of heat in the ocean then induces more tropical cyclones, and that creates a feedback that takes us into a completely different background state for the Pacific Ocean and the global climate. Now that's all very exciting. People, running experiments and running estimates, but then come Malte Jansen and Raffaele Ferrari, who say, well, the fact that you're putting heat into the thermocline doesn't mean that that heat is going to stay there for months or years, right? Because we saw this cartoon earlier, right? During storm passage, we have this warm anomaly that forms in the upper thermocline. What these guys said is, well, wait until winter comes, and you will have atmospherically driven cooling of the ocean that is going to cool down that mixed layer, and a lot of that warm anomaly, as the mixed layer base travels down and down during the winter, a lot of that heat is going to get exposed directly to the atmosphere. So you're going to lose that heat within a couple of months. It's not going to be there to be advected thousands of miles away. So they take this into account and rerun the estimates that people have done before, and they come up with a new estimate of the cyclone contribution to the ocean heat budget as 0 petawatts. So now we're in a pickle, right? Are cyclones just causing a huge effect on the background climate, or are they just causing a little seasonal bump on the temperature profiles? Which one of the two is it? We better find out. And to find out, is what I'm about to show you. We went out to the Philippine Sea. We spent, this is the Western Pacific, east of the Philippines. We spent 2 months there. And we had microstructure measurements running 24/7 off the back of the ship. This was August to September. And for the first 30 days of this experiment, the weather was pretty calm. It was sunny. There weren't many significant storms. And you can see this in this plot right here. It's a time integral of the mechanical energy entering the ocean. So our ship was here, and you'll see actually the energy input, the mechanical energy input was negative. So the ocean was losing mechanical energy to the atmosphere. But then for the second half of the cruise, we have 3 major typhoons come by the region, and these are essentially loading up the mixed layer with tremendous amounts of momentum. And through this, we get to do it before and after and see what the long-term effects of adding all that momentum to the ocean are. Now here are our measurements. This is a time series. So in the y-axis, we have depth. And the top plot, these are the hourly average velocities that we get from the ship, right? From an ADCP. In the middle row, I filtered those velocities to extract the near inertial component. And now I mentioned near inertial waves earlier. You can think about a near inertial wave as the ocean's intrinsic reverberating response to sudden forcing. So you put a bunch of momentum into the mixed layer. That momentum is going to organize into near inertial waves, and then these near inertial waves are going to propagate down into the deep ocean. And you can see that here in these measurements. You have this like barbershop pole-like pattern that starts at 70 meters and then progresses over to 200. And you can see it that before the storms, we have essentially no inertial wave activity, but after the storm, it becomes very clear. And now really the key here is, so the three columns to the right are before the storm, sorry, after the storm, left this before the storm. So before, after, really the key here is this gray shading. So that shading shows us where there are downward turbulent heat fluxes greater than 25 watts per meter squared. So how to make sense of that? You see that before the storm, there's very few gray areas. After the storm, there's a lot of them, and they overall coincide with the presence of the waves. The way to think about this ray shading, for example, here, is that, for example, in this extent that goes from 80 meters to 200 or so, what turbulence is doing there, it is promoting active interaction between the overlying layers of seawater. And it's creating this sort of drain pipe that takes heat from 80 meters depth and flushes it down to 200 meters. So that's what we're seeing. And we can plot this many different ways. So here, this panel D is the turbulent diffusivity associated with that turbulence. The green line doesn't look very clear in this projector, but essentially the turbulence is much greater after the storm than it was before. And we also have these panels for these mean profiles of the turbulent heat flux that show us, for example, if you focus on the purple line in panel E, that you're taking heat away from that layer between, say, 80 and 110 meters, between 80 and 110 meters depth, and you're depositing that warmth or that heat all the way down around 200 meters. And what that's doing, we can take a vertical gradient of this and turn it into a turbulent warming rate. What we see is that the turbulence is cooling the upper thermocline and is warming the deeper thermocline. So what does that mean? Well, so before I tell you what that means, we have to deal with the ever-present problem in observational oceanography. That is, so what? You observe this at this point, how do you know how this generalizes to the rest of the ocean? How do you know if this has a climate significance or it doesn't? To do that, we knew that the near inertial waves were the ones driving the turbulence. And we see that here, wherever there's vertical shear driven by the waves, which is shown by these here, that is where we see the peaks in turbulence. So we say, okay, models cannot reproduce thermocline turbulence very well, but they can do an okay job at reproducing the near inertial waves. So what we do is we get the empirical relation between the speed of the near inertial waves, the speed of those currents, and correlated to the vertical diffusivity that we observe. So these are, each point is a 4-day average at a different depth range. And we see that there's a reasonably good correlation here. We say, okay, we know this is a little bit goofy, but we're just going to take model output, see how the waves are across the ocean, how powerful they are. We're going to plug in this linear relationship and then infer what the effect of cyclones is on a basin scale sense. And this is what we get here. So what I'm showing you is monthly averages of the turbulent diffusivity and the downward turbulent heat flux evaluated at the 22-degree isotherm. Again, there's a monthly average. And why do we pick the 22-degree isotherm? Because once you put heat below that isotherm, you ensure that that heat is going to come up in the exotropics, right? Anything colder than that, that's cold water by global standards. So So when we plot this turbulent heat flux, this is all heat that is leaving the broad tropical warm water mass and is instead entering the water that is below, that is cold, and that is going to upwell somewhere in the Kuroshio extension or somewhere very far away from this, Philippine Sea. And when we look, so these are these in white in panel C are the storm tracks. You see that really the effect of the waves goes far beyond the storm tracks. It really, as these waves propagate away to the ocean, they take the storm's energy with them, and they make this heat transfer a known local process. So what we have in the end is we're able to redraw this cartoon that we started with, where we knew very well that during storm passage, you have cooling of the near surface and warming of the upper thermocline. But what we're adding here, and if you think back to that objection by Janssen and Ferrari, they were saying, well, you're not sure that the warm anomaly here, you're not sure that this warmth is going to be advected very far away. It might just come up in winter. Well, what they didn't know is that for weeks after the storm has come by, there's this active turbulence drawing more and more heat down from the upper thermocline downwards. So you have essentially the same scenario that happens during the storm. You have the same thing happening for weeks, but it's happening in the thermocline rather than near the surface this time. And so by the time the winter comes, a huge fraction of that heat, if not all of it, has escaped the depth of the wintertime mixed layer, and it's permanently locked into the ocean. By permanently here, I mean a couple years. So this way, accounting for the action of near inertial waves, we ensure that tropical cyclones do in fact have the ability to enhance the ocean's ability to absorb heat, and they can shape background climate. And one worrisome final thought is here we're comparing the representation of waves at different depths from observations and a high resolution model. HICOM has a 12th of a degree resolution. So you see, when we look near the surface, the green is the mooring, these observations, orange is the model. The model does kind of okay, but as you go deeper, you see that the model is it has near inertial waves that are unrealistically weak. So the model has this buffer zone that doesn't let the storm energy propagate down into the deep ocean. And if the model is not allowing that energy to enter the deep ocean, it doesn't matter how good our turbulence parameterizations are, we're not going to get the climate effects of turbulent cyclones. In a model, the effects might be transient, only seasonal. And if that is the case, it's because models are not representing the downward propagation of the waves very well. Now we're going to shift gears. I told you to allow the atmosphere to change subsurface waters, you have two options. You either bring energy down to the thermocline, or you bring the thermocline up towards the surface where the energy is. So we're now going to look at the opposite case. This is work I've done in my postdoc with Chang Li, Adam Sobel, Richard Seeger, Susana Camargo, and Jing Chul. We're submitting next week, so this is pretty much ready to go. And now, why does water flow upward in the equator? If you've taken introductory oceanography, you probably might think this is a solved problem. But I think maybe not so much. Now, why am I interested in this? So in recent decades, there's been a cooling of the cold tongue. So this here is the climatological SST for the Pacific over the last 40 or 50 years. And we see this is the equatorial cold tongue. There's cold water coming up to the surface in this region. And over time, with global warming, the rest of the ocean is getting cold. The rest of the ocean is getting hotter, pretty much everywhere, except two places, the Southern Ocean and the cold tongue here. So this is a linear SST trend. You see that it's either not warming or it's actually cooling. And that's very counterintuitive. People have been thinking about methods of how to realize what mechanism is responsible for that, especially because models fail to capture this cooling trend that we see in observations. Now, ideas of why this is happening vary quite a bit. Some people think that upwelling velocities might be increasing, so the water's coming up faster towards the surface. It is also possible that the upwelling velocities are the same, but they're just the water below is colder now, so when you bring it to the surface, it causes more cooling. And then there's also a big debate about whether this mechanism, is it contained in the equator or might it be connected to the exotropics? Say, for example, to the Southern Ocean, where water has been cooling as well. So I looked at this problem, and this is what my postdoc project was. And I thought we maybe don't have the ocean tools to take on this question just yet. Because when you think about equatorial upwelling, the explanation that most people have, and it's actually correct, but it's not fully satisfying, is the explanation from Klaus Wertke in '81. So he did a mass balance where essentially he says the winds, you have the winds blowing towards the west, they set up a pressure gradient that pushes water towards the east. And the effect of the winds is to drive meridional divergence in the surface layer. And then the pressure gradient is going to drive the opposite. It's going to drive geostrophic convergence in the thermocline. So you have in the thermocline water coming in, and the surface you have water going out. Therefore, you must have water going up in between, right? But when you think about it, this is a consistency argument. This is an argument that says there must be upwelling here. It's not an explanation for why there would be upwelling. And if you don't buy that, well, think about it. We're using the horizontal momentum equations to explain vertical motion, right? That just feels a little dissatisfying to me. And so so in ENSO theory, this is how people think about it. And I think this model sort of creates an impression that upwelling is pulled from above, right? The wind blows and it pulls water up. But then when you look at studies of interdecadal Pacific variability, people argue that this geostrophic inflow might strengthen, and in that case, you would have upwelling push from below. So which one is it? Can we make these theories of ENSO variability and interdecadal variability talk to each other? We can't if we can't get a clear answer on whether upwelling is pulled from above or pushed from below. So to answer that question, I used local available energetics. And essentially what that is you think of a fluid, it's stratified. And in the case of the equatorial Pacific, it has a tilted thermocline like this. So imagine that you redistributed the fluid so that the isopycnals, the density layers, are all flat. In that case, you've liberated, you've moved warm water from here, you've moved it up, and then you've taken cold water from here and moved it down, and you changed the potential energy of these water parcels. And in changing that potential energy, you must release kinetic energy. So we use that change in energy is the available potential energy, and it's essentially the energy stored in the stratification that allows the stratification to produce motion. You can think about it that way. So we're using that framework to study the equatorial Pacific, and essentially what we see is, imagine that we turn off the winds and that blow along the equator. What's going to happen is that thermocline tilt is going to level as it does during El Nino. And when the thermocline tilt disappears, you have, as shown in the schematic before, you're going to have water from here rise, and then water in the eastern edge of the basin go down. Now, the advantage, so we did this using this whole framework of energetics that has full full conservation laws. And really what made this approach appealing is that the conservation laws have this term that isolates W, the upwelling velocity, and that appears in both the kinetic energy and the potential energy equations, which means that this is an exchange between kinetic and potential energy. So you can think of this as the energetic cost of upwelling. You need to use kinetic energy in order to tilt the thermocline. And also when you untilt the thermocline, you would release available potential energy and turn it into kinetic. So here's really the meat and potatoes. This plot at the top is that energetic cost of upwelling in CSM2. What's interesting about this is this blue area right here. That blue area is areas where vertical motion is powered by potential energy and not by kinetic energy. Why is that significant? Well, because winds cannot generate potential energy. That means that the winds cannot directly drive vertical motion in this region. To explain the vertical motion here, the winds are no good. Instead, you need a source of potential energy. And we find that that potential energy is coming in via horizontal convergence of energy. So there's that inflow into the thermocline that Werke talked about. We're finding that convergence is actually loaded with energy that allows the water to upwell by itself without any additional energy input. And I'll explain this number a little in more detail later, but we find that it's between 20 and 50% of the energy used in upwelling that needs to come through this pathway that is supplied by potential energy and not kinetic, meaning not directly powered by the winds. And where does the energy come from? Well, we find essentially here, there's three ways you can increase the potential energy of a fluid. You can move its light water down. You can take cold water and move it upwards, or you can diabatically change the density of seawater. And so we need to find a source of potential energy, and what we find is that in the Western Pacific, there are these two sort of rows of downwelling where we have very warm water downwelling going into the thermocline, and as you put that very low density water at depth, it's going to want to come back up. And what it's doing is, this is now a meridional view. So you have upwelling in the equator and you have downwelling of warm water right next to it and between 5 and 10 degrees latitude. So the warm water upwells here, it creates this big reservoir of potential energy, and then equatorward flows bring the energy from those reservoirs that flank the equator, they're bringing into the equator, and when those two energy charged flows meet each other, they have nowhere to go but upwards. And they go upwards with the energy they were already holding. So this really what we're addressing is this upwelling that is powered by potential energy in the thermocline. It really happens only in the central and western Pacific. Once the water or the under equatorial current, once it reaches the eastern Pacific, it is now too elevated, too close to the surface to be considered light. So it's now heavy water, and you need kinetic energy to power that. So the picture we're seeing is upwelling begins powered by potential energy, and then it gets picked up by kinetic. That's your question?
Yeah, I have a question. The downwelling on the side could be due to kinetic energy.
Yes.
So basically, it's just the kinetic energy pushing the water down, and then there's a flow towards the equator, and then it becomes high potential energy, and then it drives upward.
Yes, exactly. Yeah, so it's kinetic energy from both equatorial regions is acquired from the winds, is stored into the thermocline. The thermocline transports that energy into the equator, and then there it is used to produce upwelling. And so that you were pointing to step 4 in this energy cycle that we described here. So one is thermocline driven upwelling, then the rest of upwelling is done by kinetic energy directly by the winds, potentially. In between 2 and 4, there's a very important step, which is diabatic surface heating of the water. So you have heavy water, cold water coming out of the cold tongue. If that water reached the downwelling regions without changing its density, it wouldn't be able to generate potential energy when it downwells. In order for that water to generate potential energy, its density needs to decrease. So here, really, the surface heating closes the cycle, and it allows water flowing out of the cold tongue it allows it to hold potential energy once it downwells. That's the actual estimate of the surface heating effect on the potential energy. So you're seeing at the cold tongue, we've raised heavy water to the surface, so it has potential energy, but we're reducing that potential energy by warming it up, making it light so that it can stay anchored to the surface. And we find that, so, I talked earlier about the supply of energy by the thermocline to the equatorial region. We see that supply changes with El Nino. So under El Nino situations, the thermocline is no longer tilted. So the thermocline in the Western Pacific is supplying virtually no energy for upwelling, and that's why upwelling is weaker during that time. In contrast, during La Nina, the thermocline tilt is greater, so there's a greater influx of energy to sustain the upwelling that connects, the 2 edges of the under equatorial current that crosses the basin. So to conclude, we've learned that much of the water reaching the equatorial thermocline has the ability to upwell without additional energy input. And that ability to upwell originates in off-equatorial regions and is mediated by buoyancy fluxes around the cold tongue. Now, the results are sensitive to this reference density profile, which I don't have time to get into the full details about it. But when testing the sensitivity of our results to that choice, we find that essentially what I'm going to synthesize what's here. El Nino theory is created in imagining the equatorial Pacific in isolation. But as you consider the rest of the Pacific and how the equatorial region interacts with higher latitudes, you find that a greater fraction of upwelling is driven by the thermocline. And so driving equatorial upwelling becomes more and more a matter of putting warm water down rather than bringing cold water up. So that speaks as to how the equator is intrinsically connected to the extratropics, and to understand how that upwelling might change over decadal timescales or with global warming, we need to understand how the equator and the off-equatorial regions of the Pacific are talking to each other. Thank you very much.
All right, so we have time for some questions, and I see Christopher already has his hand raised. So I'll go with you first.
So I'm a little confused by your statement that the wind can't create available potential energy. Because if I set up an adiabatic layered model, flat stratification, turn on the winds, later it has more available potential energy than it started with. But the only thing that has been putting energy into the system is the wind.
Yes. Yeah, I may have misspoken there. So you're right. The wind energy eventually gets turned into potential energy. That is true. And the point here is that when you look at the equation for conservation of potential energy, the winds are not here, right? So the wind here is, this is a viscous stress. So the wind doesn't appear directly here. So you can take wind energy to produce potential energy, but there must be some process in between.
There's gotta be vertical motion.
Exactly, it's gotta be vertical motion, so we're not trying to negate anything about working. We're just highlighting there's this intermediate step where off equatorial wind energy is stored in the thermocline, and then that energy helps the equatorial motion.
Any other, Kamazima?
Yeah, I want to go back to the map of where you plotted the extra heat going off from the tropics.
Oh, is this from the tropical
No,
cycles?
there's another one. Yeah,
Oh, okay, the tropical cycle?
yes.
Is it this one?
That one.
Okay.
Yeah, the one on the left.
Mhm.
So, and maybe let's start with even a simpler question. It's just how you process it. How do you get that map in the first place?
Yeah, good question. So I took, I think, 3 hourly output from HICOM. And then I filtered the near inertial currents from that model output. The period here of near inertial waves is about 2 days, so 3 hours is good enough. And then I take the magnitude of those waves and I put that magnitude into this linear relationship. And that gives me the diffusivity as a function of the
Correct.
speed of the waves.
Correct. So I assume you took into account that there is a fall off with your linear relationship kind of falls off at the high end. Did you chop that off? Good.
Yeah, so we did not chop off this, right? So if I understand correctly,
Yes.
like, at some point, we don't have observations to.
Yeah.
Yeah, that is true. And,
And the fit is getting poorer and poorer.
yeah. I mean, that's absolutely true, right? That's like a limitation that it's very hard to find near inertial waves of that speed in the thermocline. So if we go to. Okay, so this isotherm is at about 150 meters depth.
Right.
So if we go look at these histograms. Really 150 meters depth, you're not gonna reach 0.3 meters per second. Right, you see that? Like you might reach it instantaneously in the observations, but it's, when you think about a regional scale, you're not gonna have that type of speed sustained for a long period of time. So you make a good point, but in the model, there's not waves that are that strong at that depth. If that makes sense.
Right. My worry was when you look at the map, it's like there's such a big influence, and I was just wondering how realistic that. Not that one, the other one. Those are huge distances.
Oh, yeah, you mean like between 2 and 14?
Right.
Yeah, so turbulent diffusivity varies over a log scale. So if you look at, for example, quiescent ocean water, that diffusivity is gonna be 10 to the minus 6, 10 to the minus, about 10 to the minus 6. But then you go to an overturn inside an internal wave, and that's gonna be 1,000 times to 10,000 times larger. So within the scale of variation of turbulent diffusivity, a factor of 7 is relatively small.
Yeah, well, I was also talking in terms of spatial scale. When you
From
think
where
of
the tracks are.
between the tracks, that's huge. And
Yeah.
we can talk about.
Yeah, so maybe
Yeah.
just a quick follow-up on that. I mean, so these are, so during this time period, you have 3 different storms that have crossed through. I mean, have you looked? And I think you somewhat get at that scatter plot too, but is there a role potentially or different outcomes of maybe? It's not just the intensity of the storm that can impact, right, the mixing and the waves, but there's also the size or
Right.
maybe even the translation speed of the storm.
Yeah.
You only have 3 storms, so it's hard to look at that, but I mean,
Right.
do you have any intuition of maybe the role that some of the characteristics of the storms themselves, or even the
Yeah.
track they take could be important, right? In terms
Yeah.
of-
Yeah, absolutely. So the energy that cyclones put into near inertial waves changes with the translation speed
Okay.
of the storm and the stratification of the ocean. So here we have 3 storms. The translation speed is going to change how much energy goes into the waves and also how they propagate away from the storm tracks. So really, our measurements are not a picture of what a single storm does to the ocean, but a snapshot of what might be typical conditions during the peak of typhoon
Yeah.
season.
Yeah.
So there's some things we can't piece apart in the observations.
Yeah, so we have one question in the Zoom, but I'm gonna follow up with that point that you just made though, which is, so. To that point though, is there? Could there be prime, now I'm thinking not just in the Western Pacific now, but could there be prime areas where this effect could be larger? Meaning if you have a lot of storms that are moving over, like, is it better for them to, in terms of the effect that it might have, be in the deeper tropics, or what the effect in this example seems to weaken as they go towards north, and that could just be that the storms are. Well, maybe it doesn't weaken. I don't know. Yeah, it's maybe more of a future looking question of, are there hotspots for this that have a
Right.
particular impact on that?
Yeah, I think the Western Pacific warm pool would be a good candidate because it has the strongest storms and also the largest volume of warm water in the global ocean. But the Gulf of Mexico might also be a good place to look because it gets really, really warm, and also it's a semi-enclosed basin, so it typically doesn't have as many energy sources as an open basin would have. So it might depend more on these storms in order to be able to diffuse down the heat it gets at the surface.
So really quick, one of the questions that came in the Zoom chat, and I think that maybe I think this is probably maybe more related to the second part of your talk, but it says, it is salinity, oh my gosh. Salinity change considered in the density change during these calculations.
Yes, it is considered. I didn't really talk about it, but it is in the, it's in the code. It takes care of salinity. And so this diabatic term actually is a product of both the diabatic temperature change and also the diabatic salinity change. We just find when estimating this, it's the contribution of salinity to this term is very small, but it does show up more importantly in the estimating of the energy itself. The EA. So short answer, yes, we're
Yes,
taking
okay.
salinity into account.
Any questions? Any other? Yes.
Yeah, you spoke to some sense of motivation of some of this in representing these processes and models of climate change.
Mhm.
My question is, and the answer is probably no, is whether there's any evidence of any secular changes in these processes over observational time.
What do you mean by secular?
Time dependent, anything that's changed over the period of time in which people have been making observations.
Yeah, so over the temperature of the cold front has been cooling, right? But we don't really know if the upwelling velocity has been changing because it's so difficult to measure. And if you measure it, it's usually an indirect estimate. So I think that's part of the challenge that,
So we'll know it when we see it.
probably, yeah. There,
Yeah, a quick follow-up. Do you have any insight about the cause of the cooling trend in the Pacific?
that is a very
$1 billion question.
There's a big debate going on in the climate dynamics community about it. Some people think that cooling in the Southern Ocean is changing the temperature of water that makes it to the subsurface cold tongue. Other people think that cooling in the Southern Ocean is actually the same person thinks cooling in the Southern Ocean is creating changes in clouds that are helping the water cool. There's also arguments as to, with the greenhouse effect, you would have a strengthening of the water circulation that enhances the wind-driven upwelling. So there's so many arguments and theories. Some people think it's just natural variability. Right now, we don't have a way to really, I think, tell apart which ideas are better than the others. And I think a reason that we can't discern right now is because we've been neglecting fundamental research of equatorial ocean dynamics. But that's of course what I think, because that's what I work on.
So is there consensus from the model simulations regarding the changing of temperature there?
So the models don't show cooling here, they show warming. And so,
Multi-model.
yeah.
There are models that do show cooling, but there's a very, very small subset of all CNO models.
Yeah. And it'll be one ensemble produces cooling,
Yeah.
but then 3 ensembles produce warming. And so generally, the way people diagnose this is, what do I have to change in my model to reproduce the observed cooling? That's generally the approach.
It could also be maybe because our observations have changed, so the error could be in the observations.
That's definitely a possibility.
Right?
Yeah, satellites there, it's always possible.
So that sounds like a perfect discussion to move to lunch. So just a quick reminder that we're gonna move over to the Swanson room for lunch. Please wait for the speaker to grab their food first, just this first seminar of the semester, so we'll just go through some of the logistics. And then at 1:45, students and early career postdocs will have a chance to meet with Noel before the end of the day, and he has to leave us. So let's all thank Noel one more time.